What you're looking at over here is data from offshore Louisiana. As we pan from west to east, you can see two things that are rather challenging. One is that the stratigraphy is not layer cake, it changes quite a bit. And secondly, is based on the thin fault attribute data you can see on there, the faults are also rather complicated. They're crossing, and as you might imagine, this is due to the fact that in this particular area, the salt tectonics has had a rather convoluted history. I'm Steve Tobias with NearFX, and today I'm going to talk about Paleoscan workflows from a bit of a philosophical background. And by that I mean I want to suggest we reconsider some of the paradigms we work in. If you are in industry and if you are a geoscientist, you probably work on a G&G staff, standing for Geology and Geophysics. I think the time has come for us to think in terms of S&S. Structural and stratigraphic geoscientists more than G&G. And along that line, I'm going to talk about decoupling structure from stratigraphy, why Paleoscan is particularly good at that, and what are some of the advantages. The end game, of course, is to create an RGT model that faithfully represents the structural geology and the stratigraphy. And quite often that's pretty straightforward. However, when faults go listrict, when there's inversion and there are other complications such as crossing faults, it sometimes is necessary to take the fault model outside of Paleoscan and to use some structural geology tools to validate whether or not the structural interpretation makes sense. Let me explain why that's the case with this simple schematic. This started with a seismic section onto which I drew a fault plane as best I could, and over here there's a well. In that well there are tops, and with those tops and a synthetic seismogram, I drew in a model that overlaid the horizons over here and here and here. The big problem in Paleoscan or any seismic interpretation, for that matter, is to properly correlate from the footwall to the hanging wall. Now you might say, well, what does forward structural modeling have to do with this? And the answer is really quite straightforward. If you are going to use conventional methods, the way that that's done is you simply take a correlation polygon here, you bring that correlation polygon here, and you try as best you can to correlate across there. Using forward structural modeling gives you a very important leg up on how to do that. The reason why forward modeling is so helpful in correlation is because the shape of the geology on this side is determined almost entirely by where you put the fault. And more often than not, when a fault goes listrict, or the data quality is not that good, or there are crossing faults, the shape of that fault may not be properly placed. If that's not placed, the correlations are in danger, and the RGT model may be limited. With an interactive forward structural model, and here I'm using Structure Solver, you can modify points and put them where they may actually be as opposed to where you thought they were from the seismic. And the goal here is to modify the fault until you get a very, very good match with the overlying geology. And now you may think that's overkill, but there's a really important advantage on doing that. The reason for that is once you know the correct placement of the fault, then you can freeze the fault and refine the placement of the horizons on both the upthrown and downthrown side. By doing that, you have a very precise understanding of where the horizons expanded, and more importantly, you know what the expansion index is as a function of throw down the fault. And the reason why this is so very important is once you have an understanding of where the reflectors here correlate, and you just need to put them in on the upthrown side, they pop in automatically on the down thrown side. Once you know that, you have an independent means of correlating, which in the construction of an RGT model and Wheeler diagrams, those correlations really have to be done well. And so here, based entirely on kinematic principles, it's possible to correlate across. That's pretty powerful in some areas, not all areas, but in some areas, it's a real game changer. And so that's why I really believe that Paleoscan is a natural for a decouple-recouple workflow. And we spend a lot of time putting together the model grid so that the stratigraphy and the correlations are properly done. And now we are able, particularly with the 2019 release, which I'll be describing in more detail shortly, we're able to take a fault set, create it, take it into a structural modeling package, validate it, modify it, bring it back in a very decoupled manner. That's pretty powerful. Well, that's a pretty long-winded introduction to what the tip of the week is. The tip of the week is how to improve Paleoscan workflows by moving from a G&G, or Geology and Geophysics paradigm, to one that is SNS, which utilizes tasks that fall under the structural geoscience umbrella or the stratigraphic geoscience umbrella. Decoupling structure from stratigraphy is really the way to go, and it's really pretty easy to do in Paleoscan, as you'll see in the next few slides. The first part of the three-step process to automatically extract faults is real simple. You create, or importantly, you import a volume that enhances the faults. As you can see on the seismic, we have faults here and faults here. In Paleoscan, for a while now, you can enhance them by creating a cube that is variance cube. There's also coherence cube, chaos, fault likelihood. There's a lot of possibilities. They default to variance cube, which probably works best in some areas, but not all. The second step in the three-step process is to thin the faults. This is a really clever and amazingly powerful technique that was developed by David Hale and his cohorts at the Colorado School of Mines. And then after the faults are thinned, you can go ahead and extract them. And here you can see this is one extracted fault, that's another extracted fault. So the three-step processes are create or import a fault volume, thin it or import a thin fault volume, and then extract. And of course, the fourth step is filtering, which we'll be talking about shortly. And so here's an example from offshore Louisiana, where I've taken a three-step approach, as I've just described. I took a variance cube that we were looking at before, and then I thinned it, and then I extracted the faults. And I've displayed them in 3D on a time slice. And you can see that there's quite a bit of character over here. But you might also see that some of these faults don't look terribly geologic, and the reason is it's old data, it's public domain data, and there is an east-west acquisition overprint that has caused some noise in the direction of acquisition. What's particularly cool in this release from Paleoscan is that it's possible to display the faults according to azimuth. And not only that, it's possible to very easily filter out the east-west faults I just talked about, and the results a much improved fault set, which can then lead to a much better relative geologic time model. But that's not all. It's possible also to look at the size of the faults, and as you can see, there's a whole bunch of really small faults over here. And so on the next slide, what I'm going to do is reduce the amount of contribution from the smaller faults. And so as you can see here, I've filtered out a lot of those small faults and come up with something that's certainly not a complete fault description, but it's brought down a lot of the noise and allowed me to then take these more robust faults
and merge them appropriately and extend them appropriately. What's particularly attractive to me about this new functionality is, as I said before, Ellis plays well with in the playground with other software developers. And so in this case, I'd spent a lot of time putting together a thin fault likelihood volume in OpenDetect fault and fractures. And rather than reproducing that here in Paleoscan, I imported that. And as you can see, there's a lot more faults. And as before, you can see there is quite a bit of east-west noise that I need to take care of. And here, once again, I've filtered out the east-west values and come up with a much better solution that has a lot of small faults I need to take care of, but it seems to have a different solution for the problem. And here is this result after having eliminated, once again, all the faults below size 8. And here is a comparison of the two approaches. On the left is the thinned variance using default parameters, and on the right is thin fault likelihood, which represents a lot of effort, which could quite probably be reproduced inside Paleoscan. But the significance here is that with this release, you can build on previous work without having to duplicate everything that you've done. Now, we've been talking about azimuth and azimuth filtering, but it's also possible to do dip filtering. For example, this is a wide open horizontal to vertical inclusion of all dips. But as you can see, there really are no dips shallower than about 30 degrees or so. And sure, they go vertical all the way down here. But let's see, maybe we can use dip filtering to enhance that fault model even more. In this slide, which looks just like the previous one on the right, I've eliminated all faults shallower than 30 degrees, and it looks pretty much the same. Maybe there's one or two outliers that have been cut out. But what's nice about this new functionality is I'm able to play around and see what happens if I remove some of the deeper faults or even some of the shallow faults. Let's see what that looks like. This functionality is particularly good for geologists and those of a geomechanical mindset, because here in the Gulf of Mexico, it's really unusual to find any faults dipping greater than 65 degrees. The rocks are just not competent enough for it. So I started the next step by bringing up only those faults that are steeper than 65 degrees, and we're going to see if they make sense, and if not, we'll just filter them out of the solution. What I find is a really good approach here is quite simple, an empirical approach. Let's take a look at seismic data through some of these faults and determine if they're geologically reasonable or not, and if not, well, let's just get rid of them. Well, here's the seismic line that was just shown on the previous slide, and as you can see, some of these very steep faults are in fact not structural at all, but they tend to be artifacts that can be found at the edges of high amplitude events. So I don't like that one. Now let's look at some other really steep faults and see if they make any more sense. Well, as you can see, no, they really don't. In each case, those very steep faults seem to be artifacts of the numerical process used to create the thinned fault likelihood. So let's just get rid of all of them. While we're at it, let's take a look at those shallow faults. The really shallow faults from 0 to 36 degrees also are pretty suspect. So what I've done here is I've made two concentric circles and retained only those faults at all azimuths except east-west that are pretty shallow. Let's take a look and see if those are good or not. Well, this slide speaks for itself. A lot of those really shallow faults also seem to be related to artifacts in the processing. There are some slight exceptions. such as this one, where you have some slumping in a rather chaotic facies, looks like a mass transport complex. But in general, in the construction of my relative geologic time model, I want to get rid of all of these. So let's do that. And this is the result. I've eliminated all faults shallower than 36 degrees and deeper than 64 degrees. You can see that you can do that numerically or you can do it graphically. And here you can see I've retained only those faults in this ring right over here. So it looks a lot better, but clearly there are still some issues. Some of those faults need to be extended. Some of those faults need to be merged. And so how do we go about doing that? Well, that's actually pretty easy to do. First, first order of business is to examine the faults in 3D space, see which ones need to be merged and which don't, and then figure out a strategy to fill in the gaps that are present. The gaps that are present should be filled in on the inlines or cross lines. And here's a real quick example of doing that. And as you can see on the right, the fault plane shows you when you finished your job.
And that brings us to the summary. As I started off, I said this tip of the week would be a little more philosophical than most. And what I've tried to show is that to optimize the Paleoscan workflow, it can really help to focus on structure and stratigraphy, or S&S, as opposed to G&G, where we usually separate out seismic from logs. And why this helps is it enables us to decouple structure from stratigraphy and optimize them separately. One of the really nice things about Paleoscan is it's built exactly for this, and so that once you finish working up your structural component, you plop it right back down into your stratigraphic model and take it from there. The entire process that I just described starts with the extraction and editing of faults in Paleoscan. With the new 2019 release, that's a 4-step process. Actually, you create the volumes, or you import the volumes that are of importance, whether it's variance or fault likelihood or coherence or chaos, doesn't really matter. And then you thin them out. That's the second step. And the third step is you extract the faults. And the fourth step, which is really nice, is that you edit those faults in a very intelligent manner based on size, azimuth, and dip. Another benefit of this decouple-recouple approach is that you can then easily put in a forward modeling component, such as what I showed you using a structure solver. And what this can result in is a structural component of much higher fidelity. Not only will the faults more likely be in the right place such that they register the horizons properly over the seismic data, but more importantly to me is it can greatly improve the model by understanding where the RGT values, those timelines, really need to go, whether or not the facies on the upthrown and downthrown side of a syndepositional fault look the same, which they probably won't, and are correlable. It's very powerful stuff. NearFX offers Paleoscan interpretation work for companies looking for quality contract work in everything from international new ventures to Gulf of Mexico and North Sea field development. If you'd like to arrange for lunch and learn, please email me, Steve Tobias, at steve@nearfx.com. And if you have the time, please visit us at our website to learn some more, nearfx.com. Thank you for your time.